Today is November the 17th, 2012, and I'm going to try to document my procedures. Not that mine are the best or are always correct, but I have been asked before on how to troubleshoot amplifiers. This is a little Fender, very nice little amp. It's been refurbished by someone. They actually did quite a nice job. I'll show you quickly here. See, they took all the Tolex off. Kind of interesting. Nice and clean here in the back. It's nice to see that there are people out there that do good work. Well, I got this one at the shop because the musician said that he thought it was running hot and just wanted it checked out good. That's okay. So first thing I'm going to do, I've of course taken it out of its cabinet. I'm going to measure the temperature of the tubes with my little laser thermometer. I've already gone this far, but I'm backing up and I'm starting over. But I want to show you what I've gotten so far. Here's one. See, that one is pretty darn hot. That one's approaching 400 degrees. This one is quite a bit cooler. You can see that's a lot of difference. And if one is like 300 degrees, the other one's 310, I don't worry about it. But 260 to 400 is a lot of difference. This tube is running really hot. I've already written it down. I document stuff as I'm going through with my little charts right here with my logo and all on it. So I've written down the temperatures. I called one tube A and one B. I have run them through the old TV7DU tester over here, and it tests both of them at 44. I've written that on there, and that's pretty strong for a 606. The minimum is 25. So the tube tester says they're equal. The temperature says they're not, and I believe the temperature. Now, when I put a signal into it, I've got it hooked up here to my dummy loads up there. If you've seen any of my videos, this is redundant. So I'm going to go through this quickly. I'm going to plug in the drive, and I'll show you what it looks like. Sorry for all the fumbling here, but I need more than one hand. I'm going to crank it up. Okay, here we go. So I'm obviously overdriving it big time. See, that's it's not completely symmetrical there. Top is squaring before the bottom. It's not terrible. There's its output. 17.5 squared divided by 8. That's close to 50 watts at 9% distortion. There's its harmonic profile. There's some things in here that I don't like. Here's our fundamental. There's our second harmonic. Oops, knocking things loose here. Third harmonic. Third harmonic's big. That's not good. We don't like odd harmonics. Our ears don't like them. There's the fourth, the fifth. So we got a very large third and fifth harmonic. So that's at a kilohertz. Probably not something terribly pleasing. So we've got some things to look into. Okay. Next thing I'm going to do is we're going to come back and we're going to look in this, but not right now. We're going to flip it over and check a couple things underneath. Okay, now I've got it turned over and it is turned on. Never work with two hands on high voltage. Just don't do it. Like here I've got the negative lead clipped to ground. I'm not going to use my left hand and hold the negative lead to ground and then with my right hand start probing around in there, because I'm going to get hurt. Just don't do it. Just work with one hand. I'm holding a camera obviously with my left hand, otherwise I'd have it in my pocket. Okay, well, let's start out with pin 3. Pin 3 is the plate. I'm going to touch it right here, and here's the voltage we have, 432. The next one would be the screen, which is pin 4. and it's 431. That looks good. Let's go to the other tube. Pin 3, 430, and pin 4. That looks good. So we've got that. That's what we just found out there is we don't have an open screen resistor. These are the screen resistors out here. They're 470 ohms. They've been hot, but they're not open. We'll measure them with an ohm meter too, just to be sure. Just a general inspection. This is the high voltage power supply over here. That series of 6 diodes, and then this component in this area. Here's the bias supply. Here's the bias adjustment. There's our output tubes right there, 2 6L6s. These are the 12AX7s across here. Plate grid cathode, filament, plate grid cathode, filament, center tap. Here's our filament winding. Filament winding, we're only using half of this tube right here. You can see that plate grid and cathode of the first stage is not even used. There's the third stage. All this is voltage amplifier and tone. This is the driver that drives the 2 6L6s. This is a 12AT7. That's our 12AX7s. Okay, so our negative lead came loose. Right, here's our filament winding. You might notice there's a couple 100 ohm resistors to ground right here. That's to help reduce the hum. Everything actually looks pretty good. A really good close visual inspection with it turned off. Of course, I got it on now, but I'm going to turn it off. Is a good thing to do. Then we're going to think about it for just a second. Actually, before I turn it off, we'll make some measurements with the oscilloscope into the grid, so we're not guessing at anything. We can start guessing at things. We can say, oh, it's the output tubes, they're bad. Well, one of them's hot, one of them's much hotter than the other one, which does indicate an imbalance in the output tubes. And we can say that with some confidence because our plate and screen voltages are equal right here. Plate and screen, plate and screen. So they're both operating the same. If we wanted to prove something to ourselves and just, become overly technically involved in it, which may not be overly technically involved, we could swap the tubes. We know the temperature of them. We've written it down. We've made a note of it. We can swap them and see if the temperature follows the tubes. I'm confident that it will. So I'm not going to go through that process. Now, if I had different voltages here, then I would know that it's, it's in the circuitry and not in the tubes. So we've got an imbalance in the tubes, which may be causing some of our imbalance on the oscilloscope when we're driving it. Let me hook it back up again here. Well, you can hear it squealing. See, there it is. See, it's clipping up here first rather than down there. We'd like for it to look like that. We're going to try to get there. We probably can, but sometimes we can't. Sometimes we can't get everything we want. Right there, and look at it at a slower sweep, and you can see the ripple on the top. That's power supply hum. And again, there's our spectral analysis of it, and our odd harmonics are high. 17 volts at almost 9%. So it's actually, it's musical. It would be playing music quite loud and not offensive right now, but we want to take it a little further. Let's leave it just like this, and I'll have to stop the camera and hook up an oscilloscope probe, and we'll look at the grids of the output tubes and see if we see an imbalance coming from the driver, so we don't just start shotgunning it. Okay, now we're going to I'm on the grid of one of the 6L6s here, and this is what's driving it. That looks pretty darn good. It's not clipping. See, there's our output again. We're watching. This is the output going to the speaker across the dummy load. This is what we're going to hear. But this is what's driving the grid of one 6L6, and it is not clipping. And there's the grid of the other one, and it's not clipping either. It's not beautiful. It's not a beautiful sine wave. It's a little out of shape there, but it's not bad. It's not clipping, but our output is clipping. I'd say that's a pretty good indication that it's the output tubes. Let's crank it up a little bit more. Let's just see how high we can get it here. Okay, whoa, we can overdrive it pretty bad if we try. There we go. Let's leave it right there. We're clipping a little bit on that grid. We're clipping pretty hard over here now. Almost both top a little more than the bottom. There we go. Let's go to the other grid of the 6L6. Let's see. Let's get our amplitude up to about the same. It's always nice to. There we go. See, we're just starting to distort there. Let's look at the other one. That still looks pretty good. But now we're starting to clip both. So it appears to be that the clipping is occurring in our output stage and not our driver stage. So we're not just guessing at it by swapping out tubes. We could guess at it by, that looks pretty good. I don't think we need to work on anything from the output tubes backwards. Looks pretty clean. So let's put in a new set of output tubes and see what happens. This one's actually ending up a little bit too simple. One of the very common things, so I can go over, is that you should check is, and we'll go over this, is you should, we did check the voltage here on these points, the screen, because these resistors, if one of the tubes ever flames out and the plate turns cherry red and it just goes, things go horribly wrong, then it oftentimes burns this resistor up right here. Now, this is a, looks like a 1 watt resistor, maybe a film resistor. And you can put a 5 or 10 watt in there and it won't burn up. But then you're actually risking burning up your output transformer. It's better to let these kind of things flame out and then have a tech repair it for you than to put components in there that can't burn up, excuse me, because they're so large, and then you risk burning up other things. Let's see, one thing we might want to look at now, let's turn the volume all the way down. So we got no output anymore. Let's look at the ripple on the bias supply. I am still just working with one hand here. The ripple on the bias supply would be right here. And if we look at that over here, cranking it up, that's not bad. Nice and quiet. If we were to see, that's the maximum gain of my oscilloscope down here. Nice quiet. We would not want to see a lot of 60 cycle or 120. Well, actually it'd be 60 because it's a half-wave rectifier. We don't want to see a lot of ripple there. That would not be a good thing, and then we'd have a bias supply problem. One other thing we do want to check here is we'd like to know what our bias voltage is while we've got it upside down. I'm trying to do all this kind of stuff all at once, so I'm not turning it on and off and flipping it upside down, right side up so many times. Okay, here's our voltage. Let's look on pin 5. That's what matters. What's actually on pin 5. Minus, sorry about the glare. Minus 44.6. Might be a little low for a plate voltage of 430. And we vary the bias voltage right here. The more negative, the less current flowing through the tube. Now there is kind of a problem with these old amps, and that is they're not set up so that you can measure. I'm going to unplug it because we're going to be turning it over and doing some other things to it. The cathode on these tubes are grounded straight out, and you can see that if I can get enough light on it. There's pin 8 right there, and right there's ground. So you can't measure the cathode current. It's kind of a shame. You'd like to set the cathode current to about 35 or 40 milliamps. If you set it to 40 milliamps at 400 volts, that's 16 watts of static plate dissipation. I believe a 6L6 is about 30. I'll have to look it up. I can't remember every little number, but I think it's about 30. So you're setting it for about half. That's reasonable. Some people have different opinions of where the static, no signal cathode current should be set, but I say about somewhere between 35 and 40 milliamps at that kind of voltage. We can't measure that, the cathode current, without inserting a resistor in the cathode circuit. I'm not going to do that. You can put a 1 ohm resistor in there, and then if you measure the millivolts across the 1 ohm resistor, then that will straight away translate to milliamps through the cathode of the tube. But what we're going to do is we will make some bias adjustments. We know it's at 44, and I'll write that down so we can always go back. You want to write things down where they came from. If for no other reason, you can tell your customer what it is, and secondly, maybe you can get back to it when if you do something really dumb. Okay, yeah. One of the other things I'm going to do, I got it unplugged and it's draining now, but I will make absolutely sure it's drained. Here's a really nice little device to have. It's called a contact cleaning tool, right here. And I'm going to go through and burnish all the contacts right here like this. See, that one's already open. That's a speaker contact. I go through and spray them, and I'll burnish them with this. That's all you need to do to those contacts. I've used these things all of my working life. We used these things back in the days when I was with NASA to clean the relays and the old computer power supplies and some of the logic circuits. We used them even out at White Sands Missile Range when I was out there up through the 80s. I guess we don't use that kind of stuff anymore. I don't work on that kind of stuff anymore. But I'm just showing you what I do when I work on these things, and I'm hoping it helps. We're not quite through yet. I'm going to put some new tubes in, and we'll make some measurements, and then we'll look at the capacitors on the other side. Some people have some funny ideas that you should replace all the capacitors. That's not necessary. Just isn't necessary. These old capacitors in here, part of what gives it its vintage sound, and you start changing them out, and you shouldn't do that, in my opinion. Electrolytic capacitors, the ones that are polarized, plus and minus, they do go bad. Everything goes bad in time, but you want to be respectful to it. Again, that's the high voltage power supply over there. Those 3 diodes right here, 3 and 3 in series, that's the high voltage supply. You want to stay away from there. Thing will hurt you. Alright, let's put some new tubes in it and see what happens. Okay, well, I do have the capacitor cover off, and it does have a problem. These old capacitors, these are original. Things have been in there for 50 years, and this one right here just looks terrible. I don't know if that light helps or not. Mind if it's not too bright. Yeah, something has gone terribly wrong right there. That one is burnt really bad. So, got to back off here a little bit before we start changing tubes and having more fun. I'm going to have to actually do some real work in here. And if I'm going to replace one, I'm going to replace them all. It'd be silly not to. So this is a problem. Capacitors do have a problem, and I'm sure that that'll improve everything. I don't think it's going to improve the linearity, the symmetry rather, between the output, but we'll see. Maybe it will. Who knows? Okay, I have changed out all the capacitors. I went ahead and covered it up because it's just safer. Put a new label on there when they've been changed. Here they are. The ones I took out. The one that made me want to change them for sure was this right there. I mean, that doesn't look healthy at all. But here's an interesting thing. Didn't change much. There's its output. There's its voltage across 8 ohms and distortion. One thing it did change is look at this, at the spectral output. Very, very rich in harmonics. Fundamental, second, third, still predominant, still a really strong third, fourth, fifth harmonic. That's the only thing that's been changed since. Tubes are the same. There we go. Turn it down a little bit. Not much doubt that capacitor was bad. It needed to be changed. But it changed less than you might think, huh? Okay, let's change the output tubes. Okay, now I've replaced the output tubes with brand new 5881s. A 5881 is in many cases a direct replacement for a 606. It's not a complete, it's not an absolute replacement because the plate dissipation of a 5881 is less than the 606 GC. But these are brand new tubes, and our output is about the same. The top is clipping before the bottom. Also, interesting here is that this tube right here is running at 300 and so degrees. This one is oops, 250. Well, these tubes A and B, the hotter tube with these two 6L6s, which is what came in there. I'm not going to replace these tubes because I don't see anything wrong with them. They measure the same on the tube tester, and with brand new tubes, this is a hotter tube in this socket. I would say that there's probably some imbalance in the output circuit, the output transformer, because we've looked at the input to the grids and they're okay. They're not clipping. So I would say in some small way, not anything to panic over, that there's probably some anomaly here. Nothing that we can do anything about without replacing things that cost a lot of money. So there you go. This is one of many amplifiers I've worked on, and some of them work out really nice. Some of them just come out textbook perfect. Some of them don't, and you just can't make them textbook perfect. You do the best you can. This is not a bad amplifier. It's putting out, I always measure them at about 10% THD. If we drive this thing up to about 10% here, let's see. Now we don't want to bring it up that high. So it starts to clip, and it's clipping, looks symmetrical there, but when we get right at the edge of clipping, okay, loose connectors. If we run it up to about 10%, we get 17.5 volts. 17.5 volts. If I had a calculator here handy, I would do the math for you. It's 17.5 squared divided by 8. I don't have a calculator. That's a bit less than 50 watts. It's 20 squared divided by 8 would be exactly 50 watts. Here's a calculator. 17.5. Let's see here. 17.5 squared, 8 divided, about 38 watts. That's not bad. That's actually quite good. This amplifier is working, and it's working well, and it's working properly, and it's working sufficiently, and should be put back into service. It doesn't do its exact 50 watts, but that's just the way it is. You just can't make some of these old things perfect. Earlier, just in testing, and I would have shown you had it made a difference, I did replace the 12A T7 with a new one. Didn't change a thing. And that's it. So this is the way that I troubleshoot amplifiers. replace the obvious. You gotta fix what you find is wrong, like the bad capacitors, you know, the things that are exploded on the end. You gotta replace that kind of stuff. You can't let that go right there. But just guessing and making all these decisions that, well, the tubes are bad, and let's replace the tube, let's do this, let's do that, is just simply guesswork, unless you've got some way of measuring and visually inspecting and making decisions that way. So while this may not be the perfect textbook example of how to troubleshoot amplifiers, it's actually pretty typical. So I hope this helps.